So today I'll be going over 4.6, which is perform operations with complex numbers. So an imaginary number is the letter I, and I usually just make it like a little, with a little tail so that I know it's an I and not like a 1 when I'm writing. And this equals the square root of -1. The standard form is a plus bi. So you want to write your real number first and then the imaginary number second. The pattern for I is I equals square root of -1. So I squared will equal -1. I cubed will equal negative square root of -1 or -I. Let me rewrite that. -I. And then I to the fourth will equal +1. I think in the book they don't have many questions like this, but on older SAT tests, I don't know how it is now, but they would always ask for like I to the like 200th power. So what you would do is take the exponent, divide it by 4, and whatever the remainder is what it'll be whatever this answer is. Okay, and then the conjugate is the other half to get rid of imaginary numbers in the denominator. So one of the rules, just like with square roots, they cannot be in the denominator, and since an imaginary number is the square root of a negative number, you'll want to multiply by the conjugate so that you can get rid of the imaginary number in the denominator. Okay, so here are some examples. This one is similar to solving by using square roots. So we want to isolate the x squared, and we get x squared equals -100. So then we're going to square root both sides. So x will equal plus minus. And since the square root of 100 is 10, and the square root of -1 is I. So this would be plus minus 10i. So what you can do is actually split this up into two radicals. So square root of 10 is 10 and square root of -1 is I. Okay, here's the next one. We have 3x squared plus 16 equals 9x squared plus 4. So I'm first going to move the 9x squared over. So I get 12x squared plus 16 equals 4. And then I'm going to subtract 16. So 12x squared equals -12. Divide by 12. So then I get x squared equals -1. Then I'm going to square root both sides, so x equals plus minus I. Okay, next we want to write the expression as a complex number in standard form. So this is writing the real number first and then the imaginary number second. So for an addition problem, we're just going to combine like terms. So we're going to combine the 6 with the 5 and the -3i with the 4i. So 6 plus 5 is 11, and -3i plus 4i is I. So the answer would be 11 plus I. Next we have a subtraction problem. So first you'll want to distribute the negative. So we get -2 minus 6i minus 4 plus 6i. And again, we're going to combine like terms. So -2 minus 4, which is -6, and -6i plus 6i is 0, so our only answer is -6. Okay, next for multiplying, we're going to distribute. So 6i times 3 is 18i, and 6i times 2i would be plus 12i squared. But we know that I squared is -1, so that would be 18i plus 12 times -1. And standard form is with the real number first. So this would be -12 plus 18i. Okay, another multiplying one, but this time we're not just distributing one number, we're going to distribute twice. So first we have 5 times negative 4, which is negative 20. 5 times negative 3i is negative 15i. And then we're also going to distribute the negative 7i. So negative 7i times negative 4 is negative 28i. And negative 7i times negative 3i is positive 21i squared. Okay, so now we're going to simplify. So we can combine these and we can replace the I squared with negative 1. So that's negative 20 minus, oh shoot, sorry, this was plus 28 because it's negative 7 times negative 4. Okay, so that ends up being positive 13i plus 21 times negative 1, which is negative 21. So then we can combine these two, which will become negative 41 plus 13i. Okay, next, so standard form is when there are no radicals in the denominator. So for this problem, we have to multiply by the conjugate. So using a minus b times a plus b equals a squared minus b squared. So the difference of two squares, we'll want to multiply like the opposite sign in the denominator. So this is very similar to the conjugate for radicals. So we want to multiply by 8 minus I on the top and on the bottom because we don't want to change the problem. So on the top we're going to distribute 7i to both, so that will give us 56 minus 7i squared. And on the denominator we're squaring each part. So that's going to be 8 squared, which is 64, and then minus I squared, which is negative 1. So this would become 56 minus 7i squared. Oops, hold on, sorry. 56i, and then I'm going to rewrite that as negative 1. Okay, so then that'll be 64 minus negative 1. So then that equals positive 7, and that's going to come first in standard form, plus 56i over 64 plus 1, which is 65. So this here would be the final answer. Okay, next we have 7 plus 4i over 2 minus 3i. So we're going to multiply by the conjugate, which is going to be 2 plus 3i. So on the top, we're going to distribute the 7 first, so we get 14 plus 21i. And then we're going to distribute the 4i, so we'll get plus 8i plus 12i squared. Then for the denominator, we're going to square each one. So 2 squared is 4 minus 3i squared would be 9i squared. Okay, so I'm going to combine like terms and change the I squareds to negative 1. So that would be 14 plus 29i plus 12 times negative 1 over 4 minus 9 times negative 1. So then the top will become 14 minus 12, which is 2, plus 29i over 4 plus 9, which is 13. So this would be the final answer. Okay, next one. We have 2 minus 5i over 3 plus 2i. So we're going to multiply by 3 minus 2i. So then we're going to distribute the negative 2 on the top first. So that's negative 6 plus 4i. And then we're going to distribute the negative 5. So minus 15i plus 10i squared. And that'll be over 9 because 3 squared is 9, and 2i squared is 4i squared. Okay, so then that will become negative 6 minus 11i plus 10 times negative 1 over 9 minus 4 times negative 1. So that becomes negative 16 minus 11i over 13. Okay, and then this next one we are multiplying 3 times, so you can choose how you want to do this. You can first distribute the 6 into, or the 6i into the 5 minus 4i, or you can first multiply out the 5 minus 4i times 3 plus 2i. I'm actually going to do that first, just because it's always easier to multiply by 6i, and the numbers are going to get kind of big if I do that first. So 6i times 15 plus 10i, and then I'm going to multiply the negative 4i, so minus 12i minus 8i squared. So then I get 6i, and now I'm just going to simplify this first. So 15 minus 2i minus 8 times negative 1, so that's 6i times 15 minus 2i plus 8. So that's 6i times 23 minus 2i. And then now I'm going to distribute the 6i. So then I'll get 138i minus 12i squared. And since I squared is negative 1, I get 138i minus 12 times negative 1. So that'll become positive 12, and the whole number comes first. So 12 plus 138i. Okay, next is graphing. So we want to plot the complex numbers. The x-axis are for the real numbers, and the y is the imaginary. Okay, so for the first one we have 4i, so that means it's 0 for the or 0 for the real, so it's like 0 for x, and then we're going 4 up on the imaginary, so this right here would be 4i. Okay, the next one we have 3 minus 2i, so we're going to go to 3 on the real and negative 2 on the imaginary, so it'll be right here. So this is 3 minus 2i. And then the last one is negative 5 plus 3i. So we're going to go negative 5 on the x-axis and then up 3 since it's positive 3i. Okay, then the last section is to find the absolute value of the complex number. So for this, the equation is absolute value of z, or whatever your complex number is going to equal a squared minus b squared, or the square root of a squared minus b squared. So for number 14, the absolute value would be square root of 4 squared minus 3 squared. Oh, oops, sorry, this is a plus. So plus 3 squared. So that'll be 16 plus 9, which is 25, so that means the absolute value is 5. Okay, next we have absolute value of z equals 10 squared plus negative 7 squared. So that's going to be 100 plus 49. So it's the square root of 149. And since that doesn't break down into other numbers, we can leave it like that. Okay, next one we have negative 7 minus I. So the absolute value is going to equal negative 7 squared plus negative 1 squared. So then that's 49 plus 1, which is square root of 50. And we can break up 50. So 50 breaks up into 25 and 2, and 25 breaks up into 5 and 5. So the pair is going to come out, and the 2 is going to stay on the inside. So the absolute value is going to be 5 rad 2. Okay, last one we have just 7. So absolute value of z would equal 7 squared plus 0 squared, since there's no imaginary number. So that'll be square root of 49, which is 7.